Hello and welcome to another episode of Study Session. This one we'll be covering a topic in AP Chemistry called mass spectrometry, and that essentially is, I'm doing this one because my friend Ty asked me to, and I even got a different program for him. So I'm not using MS Paint right now. I probably will go back to MS Paint just because I think it's funny. But mass spectrometry is essentially a measure. It's a way to measure the percent abundance of different isotopes. So like if you have a sample of like carbon, for example, it's all carbon atoms will have 6 protons, 6 electrons, but some, you can the number of neutrons will vary. So the mass, or in either grams per mole or AMU, will vary as a result of the variance in the number of neutrons. So mass spectrometry is essentially a way to determine how many isotopes you have, and like what percent abundance they are of that particular sample. So like each sample will vary, but if we look at like all the data ever, so like let's say we have all the data of carbon ever in here, whatever, it all averages out to, with the relative abundance and the relative mass, to where carbon has an average mass of 12.01 grams per mole. So it's essentially just a way of finding out, how common an isotope is in a given sample, or even the whole sample if you base it off that. So that's it's a pretty simple concept. So Ty, it's actually this is a message for you. You're making my life hard because these problems are like exceptionally hard to find on the internet. So I kind of have to make them up. But yeah, so let's go ahead and clear all that. So if we have a graph, and this is typically how like mass spectrometry graphs are made. On the x-axis, so x, you will have the mass, whereas on the y, you'll have percent abundance. I'll just call that percent AB. So like let's say like we had oxygen or whatever, and this is, we'll say, that's 50. This is, and we'll just say 75, and then this will be 25. Okay, so let's say we're doing this for oxygen. Okay, and let's say this is a mass of, I'm not gonna, these numbers aren't going to be exact corresponding because I'm just kind of making them up on the fly of what that, like the actual average mass of oxygen is 16 grams per mole. But let's just assume that this is a sample that isn't. So let's assume that at 16 grams per mole, you have a percent abundance. So percent abundance. That's a really bad line. Let me redraw that. Okay, so you have a percent abundance that goes up to 50% or whatnot. And let's say at, we'll call this 16.5, you have a percent abundance of 25%, and we'll just say at 15, we have another percent abundance of 25%. So this is how a mass spectrometry graph would look. So if we wanted to find the average mass of this particular sample of oxygen, what we would do is, so the sum of all their masses with their respective percentage. So percent times mass equals your it's percent, that percent converted to decimal equals average mass. So since we have 20, so to solve for this, we do 0.25 times 15 plus 0.5 times 16 plus 0.25 times, I'm just gonna write this over here, 16.5 equals, and if we go ahead and pull out calculator, so you have 0.25 times 15 plus 0.5 times 16 plus 0.25 times 16.5, we would have an average mass of 15.875. So your average mass equals 15 point, what was that? 875 grams per mole. Okay, so that's how you solve it using the graphs or whatnot. Another way that I saw these worded, maybe I saw one mass spectrometry question on the AP Chem exam last year. So it's not that like big of a topic in AP Chem. Another way that you'll see it worded sometimes is you'll be like, or it'll say like, 70. That's a really big 7. 75% of a chlorine isotope is let's just say 36 grams per mole. What is the remaining 25% is all the same isotope. The same isotope. And then it wants you to know, it'll ask something like, what's the molar mass of the other isotope? So molar mass of other isotope. So if I quickly, my periodic table is kind of far away. The numbers are kind of small. Okay, so chlorine has an average AMU of 35.45 AMU. And then, so essentially what you do is you just work backwards. You set that equal. So 0.75 times 36 plus 0.25x. And then you solve for x. So we would do 35.45. It is 45, right? Okay. Minus point. I'll put these in parentheses. 0.75 times 36, and we take that number, we divide that divide that by 0.25, and we get that the remaining mass, or the remaining isotope, has to have an average atomic mass of 33.8 grams per mole. Yeah, so that's pretty much all there really is to mass spectrometry. You can also, so there's another thing you can do that's actually kind of handy with it. So like, let's say you have like, your graph. Oh, that was really bad. Oh man, that was annoying. Okay. So let's say you have your graph. Let me try. I can't draw straight. I need to just come to terms with that. Oh my. Okay. I said I need to come to terms with that, but I haven't. Okay. Let's say like you have your graph and like you have different masses here or whatnot, and like let's say you have like that there, that there, that there. Like let's say this is where your average, like you would have, then you could like, if you had like, if this was your sample and like your relative abundances or whatever, so like let's just say if this is 50, 50, and like this marks 25% or whatever, or not, you would be able to say that like, the majority of it is this particular isotope. So like let's say like this is like, again, oxygen, and this is 16, let's just say 17 and 18. This would never really be the case unless you concentrated it yourself and when it occur naturally, but you could say, it's 50% oxygen, 17 or whatnot. Yeah, so it's not really that big of a topic in AP Chem. It's not really like something a lot of people like. I mean, maybe there was one. It's a pretty simple topic, so they don't really test over simple things. But yeah, that's pretty much mass spectrometry in a nutshell. Hopefully it helped.